Physical Sciences session. My name is Themba Ncube. Today we are focusing our attention on the quantitative aspects of chemical change with a special focus on the mole. The term mole in itself, it talks a lot about, how exactly we quantify amount of matter. How do we know there's a certain amount of matter in a given sample of substance? So we shall talk about the mole quite a lot. Okay, what's the thinking that's going to guide our discussion for today? Okay, without the waste of time, let's look at the thought regarding today's session. Have you ever thought about what is the biggest number you can count? Okay, the moment you start talking about number, it has to do with quantifying. Okay, so what's the furthest that we can count to? So this is the thinking that we want to take off from, so that we guide our discussion in as far as what exactly a mole is all about. Is it about the number? That remains to be seen. Okay, right. So in terms of the quantitative aspects of chemical change, now when we talk about a chemical change, what exactly are we talking about? We're talking about a chemical reaction, substances reacting with each other. Now, when we talk quantitative, we want to know how much. Is it about the numbers? Yes, indeed, it is about the mole. So the mole is actually the quantity that we want to focus our attention on. Now, we'll also talk with respect to the mole in terms of mass, the numbers, in terms of quantities, as well as volume. So that's the focus in as far as today's discussion is concerned. Right. Okay. Now, one big question: how many molecules do you think are present in a glass of water? Right. This is a very, very broad question. Where do we even begin? We know that matter consists of particles. These particles can either be atoms, can be ions, formula units, molecules. So ideally, we would also remember that water consists of molecules. Now, so if we were given a glass full of water, now the question that we're asking ourselves is, how many molecules of water can we count inside that sample of a glass of water? So that's the thinking. Okay, right. Now, having said that, okay, we know that particles that make up matter exist in different forms, which is a solid, a liquid, or a gas. So for the purpose of this discussion, we made reference to water as a sample of substance. Okay, so it says all forms of matter consist of small particles. So these particles can either be atoms, molecules, or giant network of ions, of atoms, which is actually ionic compounds. Okay, so atoms, they make up what forms of matter? Atoms, they make up elements. Okay, so an element would definitely consist of atoms of the same kind. Now, molecules would be your covalent compounds and elements. Okay, so molecules will be the covalent compounds. Okay, or elements. Okay, remember we have molecules of elements, oxygen, for example, chlorine gas. So molecules are not only for compounds, but it can be compounds or elements, or a giant network of atoms. This is, in terms of the crystal lattice, an example would be ionic compounds, okay, or ionic substances. Right. So these are the particles that actually make up matter, okay, as we know it. Right. Now, so below we have a list of substances, okay? Which of the given chemical formula represents element and which one represents compounds? So the key word is element and compounds. Now, let's go back. In terms of terminology, we know elements are made up of atoms of the same kind, okay? So what you find in the periodic table of elements are actually the elements, which consists, if we are to take into account a specific example of an element, that particular element would consist of atoms of the same kind, okay? But then, on the other hand, if we speak of compounds, what exactly are we referring to? Let's remind ourselves, if we talk of compounds, we're actually referring to those substances, or that, group of substances that actually consist of, different atoms of different elements that are chemically bonded with each other. Different, that is, okay? Now, how they bond, it could either form a formula unit as in, the ionic compound, or it could form molecules. So here we are going to just classify, right? Now, if we look at copper, copper is in the periodic table of elements, okay? So copper is an example of an element. So this consists of atoms of the same kind. Which other one? We can also think about magnesium as an element, okay? But there's something interesting with oxygen, okay? O2, okay? I'll put a block on it just to show that it falls in the same category. Now, if you think of oxygen, oxygen is not a compound. Why? Because these are atoms of the same element that are bonded to each other. It is a molecule of oxygen, okay? However, these atoms are of the same kind. As a result, it represents a molecule of an element. Remember the distinction between a molecule of an element and a molecule of a compound. The difference is that in an element, it's atoms of the same kind, while on the compound, it's atoms of different elements that are chemically bonded or joined together. So this is an element, right? Now, let's look at compounds, okay? Just for distinction, we'll circle the compounds, okay? What's so special about sodium chloride? This consists of two atoms of different kinds that are chemically bonded. So this is a compound, while water is another example of a compound, okay? And again, we can also say carbon dioxide is a compound, while also copper sulfate is another compound. So those that we've put in blocks are actually our elements. So our key is such that this would represent an element, right? While that would represent a compound, chemical formula for compounds, okay? Right, so this is just about the classification, right? Okay, now elements are substances that consist of atoms of the same kind. That's how we arrived at that classification, okay, in the previous slide. And then secondly, atoms of an element all have the same number of protons. Now, if you take, for argument's sake, if we can go back, we can take copper, or let's say magnesium, for argument's sake. If you look at magnesium as an example, okay, magnesium is element number 12, right? It is a mass of 24, okay? Right, so the Mg is the symbol, where 12 represents the atomic number, which is actually the proton number, while the 24 recognizes the nucleon number, which is the sum of the protons and neutrons in the nucleus of that atom. So if we talk of elements, they must have the same number of protons. So the number of protons in all magnesium atoms is actually 12, right? Okay, that's what it simply means. And then atoms of the same element may have different masses. Okay, this brings us to another, dimension to it. Yes, the number of protons is the same, yet the mass will actually differ. The difference arises as a result of the number of neutrons. So these elements that have got the same number of protons but different masses, we call them isotopes. Okay, we call them isotopes, right? So these isotopes, they exist. Let's say we can have element X, all right, with, let's say we would say this is number 17, okay, 35, okay, and then we can have X, okay, which is 17, and then 37. Okay, you'd realize that the number of protons is the same for this element, yet the number of the atomic mass is 35 and 37. So this element X is an isotope. It has got isotopes, right? We'll talk about that at a later stage, okay? So particles of an element can be single atoms. In the example of noble gases, you can have, for argument's sake, helium as an example. Okay, so this consists of atoms that make up this element, or it can be molecules. Now these molecules, in the case of oxygen, this is a molecule of an element, okay? Hydrogen is a molecule of an element. But what's so special about these two is that these are diatomic, okay? So what do we mean when we say they are diatomic? It means a molecule of each of these elements exists, in pairs. So a unit consists of two atoms of the same kind that are actually joined together. We also have other molecules of an element which is like sulfur, in which a single molecule consists of 8 atoms that are joined together. And then we also have giant or molecular structures or network structures in the case of carbon as well as copper, right? So these are examples of what exactly makes up particles that make up matter, okay? So if we shift our attention to compounds, these are substances that consist of atoms of 2 or more different elements. Remember, the elements in a compound must be different and they must be chemically joined. If they're chemically joined together, sometimes we say that we'll describe them as being bonded to each other, okay? Right, so we'll talk about chemical bonding at a later stage, but these particles in a compound can either be molecules if they are covalent. So for molecule, it has to do with covalent substances where they share electrons so that they become stable, or giant network structures, which in most cases are ionic, right? Okay, and then we can also talk about molecules found in a compound which has got bonding between atoms. Then the word core means share, okay? So the moment you see the word core, it says there is some sort of sharing while the bonding is taking place between the atoms. So water, carbon dioxide, and this hydrocarbon. For now, let's call this a hydrocarbon, okay? Let's call it a hydrocarbon. Why do we refer to it as a hydrocarbon? Because it consists of carbon and hydrogen atoms that are chemically bonded to each other. So these are molecules because they are covalently bonded to each other, right? Okay? Now, in as far as the giant network of atoms for a compound, atoms are bonded by way of ionic bonding. We've already mentioned that. So that's the distinction between the particles that make up, an ionic compound versus those that make up a covalent compound. So if it's ionic, they give us a giant network of atoms or a compound. It could be, if it's an atom, then it means it's an element in the form of an element, right? Then compound, obviously, 2 or more different elements that are chemically joined together. Okay, then when it comes to the chemical formula, okay, remember, when we represent substances, we use chemical formulae. So chemical formulae comes from, the formula of simple elements that we know from the periodic table. Now, the moment they start to bond with each other to form compounds, be it covalent or ionic, we are able to represent the molecular formula of those compounds using, symbols, right? So an example, this is a combination of sodium and chlorine, which is sodium chloride. This is a combination of potassium and oxygen, which is potassium oxide. Take note, oxide. And then this is copper sulfate, right? So these are just simple examples. Now, the question here is, how many molecules do you think are present in a glass of water? We're talking about molecules. Why are we saying molecules while referring to water? Okay, what's the formula for water? H2O, okay? Why are we saying this is a molecule? This is a covalent compound, right? Let's just break it down so that we understand the question in the right context. So this is a covalent compound. That's why we can refer to it as a molecule. So the question is how many? And you must also remember that our focus is on quantifying, actually getting that number. And remember the first question that we asked to say, how far can you count? What's the furthest you can go? So it has to do with the numbers. Now, given a sample of a glass of water, now we want to determine exactly at the end of this session how many molecules are actually present in that sample. Let's understand that molecules, they can be either molecules of a compound or element. But in the case of water, when we talk about a molecule, we're talking about a molecule of a compound, okay? Now, the number that we're interested in is how many molecules can we count inside, that sample of water, which is, a glass full. Okay, so that's the basic idea, right? And then the question is, how many molecules do you think are present in a glass of water? So the thinking is, water, first of all, is a compound, YH2O, okay? That's our starting point. So that's the molecular formula, okay? Made up of molecules, okay? We need a method to count the molecules. We could find the mass, so now we are quantifying how heavy is, how much matter. So this is amount of matter, okay? Remember, matter is anything that has got mass and can occupy space. So mass is amount of matter, okay? So I'll put that in brackets, okay, amount, right? And we use that to calculate the actual number of molecules, right? So we will also like to focus our attention on exactly what a mole is all about. But having said that, let's just hold the thought about the number of molecules present in a glass of water as a sample, or just to, to give us something to think about in terms of quantity, okay? Then from there, after the short break, we'll try and look at the mole, which is the bigger concept. Let's take a short break for now. Welcome back to our second segment. We're still looking at introducing the mole. Now let's shift our attention to the main idea, which is about the quantity of matter, which is the mole. Right. It says here, the big question, what exactly is a mole? We need the method actually to count very big numbers of atoms and molecules. Remember, the first question was how far can you, what's the furthest that you can count in terms of numbers? Now, while we introduce the mole, let's think about, a better way of us counting, very big numbers. Okay, so the unit that is used to measure the amount of matter, because matter consists of, small particles. Matter consists of small particles. So we are saying that there is, a large number of particles that make up a small sample of matter. So the unit that is used to measure the amount of matter is the mole. So MOL for mole is the shortened version. So you'd use mol to represent the mole, okay? So 1 mole represents a very large number, okay, of particles that make up a substance. What makes up a substance? It can be atoms if it's an element. It could be molecules if it's an element or a compound. It could be atoms that make up a giant network of atoms, okay? Right. And then we are also saying that the mole is actually the basic SI unit of quantity of matter, right? That's the main point. How do we quantify matter? We use the mole. So the mole represents the SI unit of matter in terms of amount. So if we talk quantity, we are referring to amount. So in any discussion that involves the quantity of matter, we shall use the mole. That's the long and short of it, okay? Right, so that's what exactly a mole is. So by definition, a mole of a substance is the quantity of matter that is the same number of particles, okay? These particles can be atoms, ions, or molecules, as they are in 12 grams of carbon-12, right? So if you go to your examination guideline, it simply spells it out that definitions are very, very important. This is one of the most important definitions in chemistry, because everything that has to do with chemical change, a reaction, it is about the mole. Anything that has to do with the amount of matter or quantity of matter or whatever substance, it's about the mole. So what is a mole? It is that amount of matter which represents the same number of particles that has got the same number of particles in 12 grams of carbon-12. So the sample is, the mass of the sample is 12 grams, which element? Carbon, okay, which has got a mass of 12. So that's what a mole is, right? So remember, so carbon becomes our, our point of reference, okay? Then we are also saying how many atoms are present in 12 grams of carbon, of carbon-12. This number is 1 mole. So if we're saying 1 mole, a mole is actually a number. So yes, we say number of moles, but we are actually recognizing the fact that when we talk of a mole, we talk about a number of particles of any substance. So a mole is actually a number, okay? But it's a very big number. Why are we saying it's a big number? Because matter consists of minute particles that are very small, for us to even see via using our naked eye. Remember in the example or the big question that we asked to say, in a sample of a glass of water, which is full, how many molecules are there? So we want to immediately think of a very big number. So a mole represents a number. All right, okay? So how many atoms are present in 12 grams of carbon-12? So this number is 1 mole. The number of atoms is equals to 1 mole. So 1 mole is the number of atoms in this case, okay? 1 mole is the number of atoms present, okay? All right, so the emphasis is that a mole is a number. So 1 mole is a number, just like we say 1 dozen, it's a number, okay? Which gives me, which immediately reminds me, so if we talk about a dozen represents a number, okay? That number for any, whatever material you are talking about, it could be 12 units. So 12 units is a dozen, hence a dozen represents a number. Similarly, a mole also represents a very big number of particles that make up a substance, right? Okay, and then the question is, how many particles are there in a mole of a substance? So 1 mole of carbon-12 has 6,02 times 10 exponent 23 atoms, okay? So this is the number which represents 1 mole. So this is actually 1 mole. Much as we can say 1 dozen represents 12, okay? But why are we saying atoms while we refer to carbon? Because carbon is an element. Remember our exercise on classification of matter. If the particles that make up matter are atoms, then that matter is actually in the form of an element. Okay, let's break this down. If we say 6,02 times 10 exponent 23, we are actually saying, how many zeros can we count here? I think it's a very huge number. I don't even know how to say that number out. But in other words, we've got 602,000. This is 602,000. We multiply it by a million. Whatever we get, the product, we multiply by another million and another million. This represents the number of atoms that actually make a mole of any substance. Okay? So the number that represents a mole of any substance, 6,02 times 10 exponent 23. Okay, it can be whatever. It can be atoms, it can be, molecules, it can be, ions. It could be anything, but the number that represents a mole is actually 6,02 times 10 exponent 23, right? Okay, and then this brings us to a very, very important part of our discussion. We have spoken about a number that represents a mole, okay? So that number is called the Avogadros number, okay? Avogadro, that number is named after somebody's name. And this number is actually the same, okay? So a mole of any substance contains the same number of particles, okay? 1 mole, okay, of any substance is equals to 6,02 times 10 exponent 23, okay? Particles, whatever that is, okay? Particles, we agreed that it can be atoms, molecules, ions, formula units, it doesn't matter. So this is the number that represents a mole. So this mole is the same for any substance. So like we're saying, a dozen of bread represents 12 loaves, a dozen of eggs represents 12 eggs. So a dozen is the same number for whatever, substance you choose. Similarly, with the mole, the number remains the same. It doesn't change, all right? Okay, so the Avogadro number, the symbol is Na, which stands for Avogadro number. Take note of the symbol, okay? Is the name given to the number of particles in a mole of any substance. That's our emphasis. So this is our constant in as far as the mole is concerned. What does it mean? It says that the Avogadro number is 6,02 times 10 exponent 23 per mole. This represents per mole, okay? Per mole. So it means in 1 mole, there is that number of particles. whatever the type of particles make up that form of matter. Okay, right. And then we're still looking into the question now, I would say, what is the mass of 1 mole? Okay, now we know that how many particles make up a mole? So a mole of any substance, okay, represents, of any substance has a number which is constant, okay, of particles which is constant, okay, has a number of particles which is constant, right? Okay, so if that's the case, and that number is the Avogadro number, Avogadro number 6,02 times 10 exponent 23 is positive 23 per mole. Okay, it means then in 1 mole there is that number of particles, right? So we know that if that's the case, we know that atoms of different elements have got different masses, right? Let's go back again. What are we saying? If we choose a different element from, let's say we've got sodium and then we've got magnesium. These are 2 examples. Each one of them is made of atoms of the same kind. However, by comparison, if we look at atoms that make up magnesium and compare them to those that make up sodium, they are different. So the mass of each atom will differ for the 2 elements. However, the number of atoms, no matter how different they are in terms of mass or size, that make up a mole will remain the same. Why? Because the Avogadro number, which is the number of particles, is constant. So that is an Avogadro constant. So if we go to our table of physical constant, you'll see the Avogadro number is listed as one of the constant. It means that number doesn't change, right? Okay, so our thinking is that atoms of different elements have got different mass. It's a given, okay? But 12 grams of carbon-12 is 1 mole. Okay, that is the standard for comparing masses. All right, so that's the main idea. All right, now let's talk about relative atomic mass. All right, so the relative atomic mass of carbon, remember carbon is our standard, it's our reference. It's actually the average mass, okay, of carbon atoms based on the distribution of isotopes, okay? So if there are, different atoms of the same element that have got different masses, right? If atoms of the same element with different masses, now the average of that will give us our relative atomic mass for that particular element. So this is the relative mass calculated using the mass numbers of each isotope. So isotopes, we're saying same atomic number, right? Same atomic number, but different atomic mass. Different mass, but for the same element, okay? Right, so the units of relative atomic mass is atomic mass units. So that AMU stands for atomic mass units based on the mass of each of those isotopes, right? So then the other concept that's very, very important is the molar mass. So the molar mass of any element is actually the relative atomic mass of the element measured in grams. So what are we saying here? Relative molecular mass is actually measured in grams, because we talk about mass as, amount of matter in a sample of a substance, okay? So the molar mass or the formula mass, so the terms molar mass and formula mass can be used interchangeably to refer to one and the same thing, okay? So the molar mass of any compound is the relative atomic masses of the elements in the compound added together in the ratio of the chemical formula measured in grams again. All right, right. So, and then the question on how moles relate to mass, okay, because we've spoken about these quantities one at a time, but how exactly do they come together? So a mole of carbon-12 has a mass of 12 grams, okay? So if we calculate the moles, we are saying that N stands for moles, okay? Then small letter m stands for the mass of sample of substance. It could be a glass of water, whatever mass it is. And then the molar mass is the one that we get from the periodic table of elements by calculating, the total molecular masses of each of the substances that make up a compound, if that is the case. Okay, so if we talk of a mass of 12 grams, so 12 grams is actually the mass of the sample, okay? 12 grams is actually the mass, all right? And then the molar mass of carbon is 12 grams per mole, okay? So it's 12 grams per mole. So this is molar mass, right? Now, mathematically, the equation moles is equals to mass over molar mass. That's how we determine the moles in a sample of substance. Take note, I'm saying moles because it's a number, okay? We're asking ourselves how many moles of a substance are present in a given sample. How do we determine that? For us to get the moles of substance in a sample, we must ask ourselves, what is the mass of this sample, okay? If we know the mass of the sample or is given, we ask ourselves yet again, what's the molecular formula of that, or the molecular mass? So the molecular mass of this substance is actually derived from the molar masses of each of the individual elements that make up that substance, if it's the case of a compound. Okay, so take note, this is a very, very famous equation that we will use many times in chemistry. So take note of it. It shall be given to you in your data sheet. Make sure that you can identify it and as well as use it appropriately. So if we have got grams, which is the mass, and the grams per mole, so that those grams will take care of each other, what remains is a mole. So a mole of carbon-12 has a mass of 12 grams. Okay, let's go over that again. A mole, which is how many, that number, which is 6,02 times 10 exponent 23. If we're talking of carbon, 1 mole of carbon, which contains that number of particles, which is a constant, has a mass of 12 grams. That's the idea. So if the moles is equals to mass over molar mass, so in other words, a mole of any substance is actually has a mass of, the sample of that mass is the same as that of the molar mass of the substance. So the 12 over 12, that gave us 1, okay? So take note of that as well, okay? Now, how many molecules do you think are present in a glass of water? That's the big question that we started with, okay? We want to go full circle. So we could find the mass of water, okay? Why are we interested in that? We can say, for us to find the molecules, first of all, we start with the formula, okay? From this formula, we are able to determine the molar mass, okay? Okay? We are able to determine the molar mass from the periodic table, all right? Okay, which is 2 atoms of water, of hydrogen, and an atom of oxygen. They make up a molecule. Now we want to know how many of these are present in a glass full of water, okay? So the mass, how is it important? We know that number, that N represents the moles, okay, is equals to the mass of sample of glass of water over the molar mass. So this will give us the molar mass of water, okay? I usually say that it's small m, big M. So the smaller m represents the mass of sample, while this one represents the molar mass, okay? Right, so this information will allow us to get the moles that are present. And we know that each mole contains a same number of molecules because this is a compound, okay? So if we can find how many moles are present in a glass of water, given the mass of water in that sample, we are able to determine the actual number of molecules, which is a big number, but that big number is actually based on the SI unit of quantity of matter, which is the mole, okay? So that's what we are particularly interested in, okay? So we shall use the mass of water and use that to calculate the moles of water, okay? This is what we're talking about, okay, that are present. But how do we get from moles to number of molecules, right? How do you get to moles to number of molecules? Now, we know that a mole contains, so 1 mole of water, okay? 1 mole of water, okay, it has Avogadro number of molecules, okay, which is 6,02 times 10 exponent 23 molecules. Right. So this is our point of departure. We are saying a mole of water has that number of molecules. So if we can, by whatever way, determine how many moles are present in that, we are able then to determine the number of molecules that are present in that glass of water. So that's the thought. Let's just hold it for now, or at that point. And when we come back to the third and final segment, we shall carry our discussion further in terms of exactly how do we quantify the number of molecules in a given, sample of substance. Let's take a short breather for now. Welcome back to our third and final segment. We're still talking the mole. Okay, so the idea of a mole is that it has to do with the amount of matter. So we're saying a mole of any substance has got that constant number of particles, and this is actually the Avogadro number, right? So that's our Avogadro number, okay? So this number is constant, it doesn't change, okay? So this is the number of particles. Whatever particles can be, it can be atoms, right? It can be molecules. It can be ions. It can be anything, okay? But the number is constant. So in an element, the particles are atoms or molecules, if it's a molecule of an element. In a compound, the particles are molecules or formula units. These are ionic compounds, or it could be ions, right? Okay, so how moles relate to number? So we are saying that if we are given the number of particles and we want to determine how many moles, we must know that for every mole there is an Avogadro number of particles. So this is kind of straightforward to say that the number or the moles present in a sample depends on the number of particles versus the number per mole, which is the Avogadro number. So this is our constant 6,02 times 10 exponent 23 per mole, right? So in this case, we've got number of particles, and then this is the number of particles, okay? So that's our number of particles, okay? Say, for argument's sake, we are talking about a dozen. For us to say how many dozen, we say how many units are there, and then we divide by 12. In this case, we divide by the Avogadro number, which represents the number of particles per mole of any substance. Okay, and then let's look at shift our attention a little bit and look at gases and see how it relates to gaseous substance in terms of quantity of matter. Okay, so a sample of an element or compound in a gas phase has a fixed mass. So we always talk about a fixed mass of a gas. So this phrase will be very common: fixed mass of a gas, right? But we know that gas particles, they move very fast, they've got high kinetic energy, they fill all the spaces, but what doesn't change is the mass. So if we say the mass is fixed, we are saying that it's constant, okay? So the amount of matter that makes up a gaseous substance is the same. It's constant, which is the mass. So the volume of the sample can change depending on the temperature and pressure. This takes us to something very important to say that, the pressure of a gas depends on how fast the particles are moving, and how frequently they collide with each other, as well as with the walls of the container, which contributes to what we would know as the pressure of a gaseous substance. So that would depend on the temperature, okay? Right. But where are we going with this? We talk of standard conditions of temperature and pressure. So standard temperature is 0 degrees. This is Celsius. This is set at 0. So when we talk about a standard temperature, we're talking about a temperature of 0 degrees Celsius, right? Now, standard pressure, 101.3 kilopascals, which is also equal to an atmosphere, which is 1 atmosphere, right? So this is STP. So at a particular for a particular gas at a standard temperature and pressure, the volume of a gas will be a certain amount, because the volume depends on temperature as well as pressure, right? Okay, so Avogadro law, what does it say to us? It says that any sample of an element or compound in a gaseous phase, but remember, this is about gases, with the same volume at the same temperature and pressure will contain exactly the same number of particles. So what are we saying here? At standard temperature and pressure, the volume occupied by any gas or a mole of any gas will be constant. That we call the molar gas volume. So what is a molar gas volume? It is the constant volume occupied by 1 mole of any gaseous substance at standard temperature and pressure. And if we talk about a mole of a gaseous substance, how many particles make up that gaseous substance is the Avogadro number, which is the 6,02 times 10 exponent 23 per mole, right? So at STP, which is at standard temperature and pressure, 1 mole of a gas occupies 22,4 cubic decimeters. So that's the volume. So VM stands for molar volume or molar gas volume, right? Okay, how moles relate to number? So at STP, 1 mole of oxygen gas occupies that volume. But now let's agree that if we talk about a mole of oxygen gas, it has got a fixed mass. So this mole contains 6,02 times 10 exponent 23 molecules, okay, of oxygen. Okay, so that's the number of molecules present in 1 mole. So what's the volume that it will occupy? But to qualify this, it must be at standard temperature and pressure. That volume is 22,4. Hence, we are saying the molar volume at STP, it's actually the volume occupied per mole. So this stands for per mole or 1 mole, all right? So a mole of any gas at STP occupies a constant volume. That's the main point, right? Okay, so given a sample of gas at STP, which is the volume, knowing that each mole occupies a constant volume, then it takes us to this equation which says moles of a gas is equals to volume divided by the molar volume. So this molar volume is 22,4 cubic decimeters per mole, okay? While this is the volume of gas, okay? This is volume of gas in cubic decimeters, right? So this will be in cubic decimeters. That's why the cubic decimeters for the volume divided by the cubic decimeters per mole, okay? These will cancel each other. We're left with over per mole, which will give us the mole, okay? This is actually in moles, okay? Right, so that's the main idea, okay? All right, having said that, let's look at practical examples. How do we calculate the molar mass of a substance? How do we know? First of all, we need to identify the fact that in the first question, oxygen gas, we need to understand what is the formula of this substance, O2. It's a diatomic element, okay? Which exists as a molecule. And each one of them has a mass of 16. So if we want the molar mass of oxygen, okay, it's equals to 2 multiplied by 16, because each one of them is 16. Then this would give us 32 grams per mole. Okay, that's the molar mass. What about water? Molar mass of water, okay, is equals to, the formula suggests that there are 2 atoms of hydrogen for every oxygen atom. Okay, then this tells us that it's 2 multiplied by 1, because there are 2 hydrogen, plus 16, okay, which gives us what? 18 grams per mole, okay? So that's the molar mass of that, those 2 substances, okay? So we've done that, okay? Now the question says, how many moles of oxygen are present in a sample that has 22,4 grams? Now, we want the moles, okay, which is the quantity, right? And we know that each mole has got 6,02 times 10 exponent 23. So if we are looking for the number of moles, or the moles rather, okay, we are saying that moles, and sometimes we say number of moles, but actually this represents the moles, okay, which is a number after all. It's mass of sample divided by molar mass, okay? Now, do we have the mass of the sample? Yes, it's 2,4 grams, all right? Even if you don't put the units, we know that N is in moles, okay? Now, we have also calculated the molar mass of oxygen and found it to be, if we can go back quickly, the oxygen is 32 grams per mole, okay? So the molar mass of oxygen is 32 grams per mole. So this is divided by 32, okay? So whatever we get will be in moles, all right? Okay, so if we go to our calculator, this gives us 2,4 divided by 32, okay? Divided by 32, okay? That is a decimal fraction, 0,075, okay? 0,075, 0,075, okay? So this is less than 1 mole because it's not 0.075, okay? So this is the quantity of moles that is present in that sample, right? And then how many moles of oxygen are present in that 22,4 cubic decimeter, okay? We want the number of moles, we're given the volume, all right? But here, what do we have? We've got the volume of oxygen that it occupies, but we know that a mole occupies what you call 22,4. So we know that N is equals to volume of sample divided by the molar gas volume, right? Okay, so the volume of sample that we're given here is 2,4, okay? Cubic decimeters. It's no longer the mass. Take note of that because that's the volume of the sample, okay? Divided by, we assume that this is at STP, okay? So if we assume that this is at standard temperature and pressure, we know each mole will occupy 22,4, right? So we are looking for the moles that are present, okay? So this works out to 2,4 divided by 22,4, right? So this gives us that number of moles, which is 0,12, right? Right, so this is equals to 0,12, all right? So N, which is the moles, 0,12 mole, all right? So this is the amount of moles that are present in that sample. So the idea is actually to work out the number of moles, but it depends what you're given. From the two equations, if you are given the mass, then we'll use the molar mass. But if you're given the volume and it's a gas at standard temperature and pressure, we can use the molar gas volume, okay? Either way, it gives us the number of moles, or the moles, actually to be precise. So the idea of quantifying matter is we arrive at a point that it's always about the mole. Okay, so and each mole contains the same number of particles. So that's the main idea. So in the big question of how many molecules of water, once we are given the mass of water, we are able to use the molar mass of water to determine how many moles. And then from there, if we have the moles, we'll multiply by the number of particles per mole to get the actual number of molecules in that sample of water. So that question, if you think of it, it's actually doable in the sense that now we understand that in terms of quantifying matter, everything is about the mole. Having said that, this brings us to the end of our session for today. From myself, Themba Ncube is cheers and bye-bye for now.